Meet the leaf blower team. Morgan, the spark plug. Johnny, the flywheel. Sophia, the carburetor. Zin, the piston. Grace, the muffler. Today, we will be analyzing the fluid flow through a leaf blower. This flowchart shows the movement of air through the system. When the user pulls the starter grip, the flywheel is activated, sending current through the pickup to the spark plug. The gas-air mixture from the carburetor is ignited in the engine, which propels the impeller. While ambient air is sucked into the pump, a pressure difference occurs, shooting the air at a high velocity through the blower tube. We will start by doing an analysis of the centrifugal pump.
The centrifugal pump, which is driven by the two-stroke engine, creates the airflow to blow away leaves and debris. Air enters the system at the low-pressure region at the center of the pump. As the impeller blades rotate counterclockwise, the fluid is accelerated towards the outside of the volute as demonstrated in the diagram. The fluid then travels from the narrower to wider region within the volute casing, effectively exchanging velocity for pressure, causing a larger pressure difference. In order to compare this centrifugal pump to other pumps, we needed to calculate the specific speed and specific diameter. In order to find these values, we started by calculating the pressure difference. The power of water was calculated from P brake, assuming 60% efficiency. Then, using the relationship between power and volumetric flow rate, we solved for a pressure difference of about 5.8 kPa. To calculate the density, we first needed to calculate the outlet temperature. We used the ideal gas law and assumed constant volume while inside the pump, as well as STP conditions at the intake. This resulted in a T outlet of 305 Kelvin, or around 89 degrees Fahrenheit. A density of 1.224 kilograms per meter cubed was calculated using the same method.
To find the operating speed of the engine, we used the chemical formula for the combustion of gasoline in air. First, we calculated the enthalpy of reaction to be about 5,470 kilojoules. Using dimensional analysis and assuming 20% thermal efficiency of the engine, we can solve for the flow rate through the engine. To find angular velocity, we then divide our flow rate by the bore stroke volume, which was calculated using measured dimensions of the piston. Finally, we convert this to RPM and we get slightly over 3,000 RPM. Using all these values, both calculated and provided, we were able to solve for a specific speed of 0.25 and a specific diameter of 6.56. Comparing our values to the chart above, we can see that our pump is in the range of other centrifugal pumps. However, our specific speed is lower than that of an efficient pump, as demonstrated by the red dot, which lies below the band of points. To increase the efficiency of the pump, we would have to increase the diameter and RPM. Both are not feasible changes due to the space constraints and engine selection. We will now analyze the carburetor.
A carburetor is a device used to supply a spark ignition engine with a mixture of fuel and air. The carburetor consists of two valves, an inlet valve that is manually actuated, also known as a choke valve. This valve regulates the amount of air coming in. And we also have an outlet valve known as a throttle valve, which regulates the amount of air and fuel mixture that go into the engine. Inside the carburetor, there's a venturi connecting the inlet and outlet valve. Due to the decrease in area from the inlet to the throat, by conservation of mass, the velocity of the air increases as it travels from the inlet to the throat. This causes a pressure drop, creating a vacuum that makes fuel travel from the fuel reservoir to the throat of the venturi, where it mixes with the air. In our analysis of the carburetor, we calculate this pressure difference.
Using dimensional analysis, we calculated the outlet velocity as the product of the RPM found from the combustion of gasoline, the displacement, and the measured cross-sectional area of the outlet, obtaining a flow velocity of 8.05 meters per second. Applying the continuity equation, more specifically conservation of mass, we can find the velocity at the inlet, which is very close to the outlet one. To find velocity at the throat, we are assuming an inlet to throat area ratio of 0.7. Doing this, the throat velocity we found is 11.60 meters per second. Using the average of the speeds inside the carburetor in SSL conditions, we found the Mach number. The low Mach number obtained justifies the use of the incompressible flow assumption, since it is well below 0.3.
We also wanted to make sure we could use the inviscid flow assumption. Since the fuel mixture consists of mostly air, we used the viscosity of air to obtain Reynolds numbers above 10,000 at both the inlet and outlet. Therefore, we're able to use the inviscid flow assumption for our analysis. To calculate the pressure difference created by the throat inside the venturi, we used Bernoulli's equation along a streamline for the flow from the inlet to the throat. As we expected, this pressure drops from the inlet to the throat, and the difference is relatively low at a value of 42.14 pascals. This makes sense because we're dealing with very low speeds. All of this analysis comes together to create a leaf blower that will definitely displace the leaves from your backyard.